Hello, welcome to my mini practice presentation for my instrument acquisition proposal for a soft material flow sensor. So before I get into exactly what the sensor is, I think it's important to understand what micro air vehicles are because these sensors attach to micro air vehicles. And if you don't understand what a micro air vehicle is, I think it makes it kind of hard to understand the need for the sensor. So micro air vehicles are unmanned, remotely controlled air vehicles that are very small, usually the size of a hummingbird and the weight of a medium-sized tomato, and can travel up to 10 meters per second, which is pretty fast. And the purpose of these instruments are to gather information about terrain that is unideal for manned aircrafts or larger aircrafts. And these instruments collect information about weather patterns such as temperature or wind speeds, as well as just surveying or sort of GPS information if you attach cameras and other things to it. For this reason, to collect all this information, they need to be small, quick, durable, sensitive, lightweight. And this proposed instrument, the soft material flow sensor, has all of these qualities as well as a low need for power, so it can run on very low power. The novelty of this instrument lies heavily in its simplicity, both of its operation as well as its design. There's minimal complexity to its design, and it can be made using common laboratory tools, which makes it optimum for many different fields of science. The materials are made of soft, more flexible materials in comparison to traditional, more rigid materials, and therefore can withstand deformation of high and low temperatures and can withstand a little bit more impact than some of those other instruments. The materials are also piezoresistive, which is a decreased sensitivity to mechanical strain. So using these piezoresistive materials allows for the flow velocity to be calibrated to the resistance change of the sensor. All of these things make it a more cost-efficient alternative to other micro air vehicle sensors. There are so many different applications for this instrument. Instruments like this collect information about elastic filament velocity and are therefore known in the math area as elastic filament velocimetry. EFVs, which is just a novel method of measuring the velocity of liquids and gases. The sensor is made up of electrically conductive nanoscale ribbons that are suspended with silicone supports and create like a sort of suspension bridge. So you can kind of see the nanowires all on this plate of silicone, and then there's silicone on top of it, which then when squished together, you cut them into ribbons, and then now these ribbons are individually suspended. The sensitivity and simplicity of this instrument make it optimum for large-scale commercial and industrial use. This is Dr. Marcus Holtmark. He is an assistant professor at Princeton University. He has his background in biomechanics, biomaterials, and fluid mechanics, and he is the principal investigator for this project. He currently works with some different PhD student groups on different projects, and his graduate research is focused on turbulence and the measurement of turbulence, but his current research is focused on the development and characterization of sensors for measurements of flow parameters and atmospheric monitoring. And he says about this instrument, you can put this instrument in water and air, and the same sensor does a very good job in all of them. So it's very multi-useful. One thing that I wanted to mention before I go on actually is that this whole project was actually born out of a failure. They were actually trying to figure out or create a sensor that could measure temperatures at high altitudes. But when they were getting their data back, everything was all backwards and jumbled up, and they couldn't really understand why, and they eventually realized that this was because they were measuring the fluid velocity, which is actually something that's much harder to calculate, much harder to do. So instead of scrapping this project because it had nothing to do with their original thesis, they decided to go with it and kind of take this novel approach, this new way of measuring fluid velocity, which is kind of cool. I wanted to kind of, from that, hit the progress of this experiment, or like experiments that have been done in the past that are referenced in the original paper. The first would be the artificial lateral line sensor, which was inspired by neuromasts in fish. Scientists found out that there were clumps of hair in the ears of fish called neuromasts that water, when passed through, would help them determine the speed of the water going by them. So scientists recreated these using rigid and metallic materials to create a sensor that was pretty much the same. Out of that, much later, scientists opted for a more soft method or a softer approach, and instead used spider silk as the sensing element instead of rigid materials, which led us to Dr. Holtmark's research, which is in using ribbons of silicone and nanowire to measure velocity via the strain gauge. Some of the most important papers from my annotations to help me kind of understand this topic were from Dr. Petrica and Dr. Sartori. Dr. Luca Petrica is a professor in Rome at a university which I am bound to butcher the name of, so I'm just not going to say it. But he wrote a paper on micro and nano air vehicles. He is an expert in design and fabrication of micro machinery and has been for the last 30 years. And his paper provided a really great layout of the necessary instrumentation for micro air vehicles, how they work, their impact and importance, and yeah, just their general operation and design, which is really helpful in understanding then where the sensors kind of come in. Dr. Sartori, on the other hand, Dr. Danielle Sartori is a professor at the University of Colorado in Denver. And she specializes in fluid mechanics and fluid micromeasurements. And her source detailed micro air vehicles as a starting point for fluid censoring and kind of improving the efficiency of micro air vehicles, which I thought was really important to this because it's like we now that we know how they work, how they're made, we kind of need to know how to optimize the efficiency of them. So kind of where to start for that and how to do that. Before this instrument is released to the public, I think it's really important to do some further research on these three areas, one being sensing capabilities, other manufacturing methods, and lastly, mechanical properties. So the sensing capabilities I would do further research on because there's high uncertainty and time lag associated with the instrument, which restrict its applicability to some different uses. And further research into the sensing capabilities could determine better fabrication techniques to lower those uncertainty and lag times. Next, I would also put money into finding a more uniform manufacturing method, which could reduce error and drag coefficients and would allow for further calibration that could also reduce error. Lastly, I would look into the mechanical properties of the ribbon. Long-range sensitivity could be easily tuned by modifying the stiffness and also the thickness of the ribbon, as well as the piezoresistivity of the ribbon. So altering these things could lead to more optimum parameters, which could change the necessary bandwidth or resonance for different applications. The market potential for this instrument is so vast. It would definitely lower costs for different instruments. There are some flow monitors that are upwards of $10,000, and one of these sensors costs less than $1. So, and it has so many different uses, so it could replace instruments not only by cost, but also just by how many uses it has. It also has an increased efficiency. It's highly durable because of the soft materials that it is made out of. It's also got a sensitivity of down to 4 meters per second, and therefore it can be adapted I messed it up, but it's okay. The sensitivity of the new sensor is also only limited by the dimensions of the ribbon, and because those parameters can be changed, it can also be specially adapted to specific applications. It also requires low power and um, can be made with lightweight materials found around the laboratory, which also kind of increases efficiency and saves time. And like I've said, it's got innumerable uses. It can be used in so many different liquids and gases. I'd say not all because we haven't tested them in all, but from the ones we have tested them in, that it has been tested in, it's done great work. The low cost and high durability of the soft material flow sensors make it an innovative replacement for other micro air vehicle sensors that are less efficient machines in general. And investment into the research and development of this instrument could result in breakthroughs that would positively impact so many other fields of science and have such a great breakthrough. So thank you for your eyes and ears, and I hope that you truly consider this low risk, high reward investment opportunity.